we have talked about EMF initially, and we said we are going to elaborate more on EMF. What do we mean by EMF of a cell? When we talk about EMF, it is simply the voltage possessed by a cell when it is not delivering any current to an external load. So the inbuilt energy in a given cell when the cell is not delivering current is what we refer to as EMF. It is otherwise called electromotive force. So you can also say that it is that inner energy that is available to do work. That is what we refer to as EMF. And how is the EMF of a given cell calculated? It is calculated using a formula: electropotential for reduction half cell minus the electropotential for oxidation half cell. Or we can say the electropotential for cathode minus electropotential for anode, because oxidation takes place at the cathode while reduction takes place at the anode. We can also say it is electropotential of right hand side minus electropotential for left hand side. That is actually how to calculate EMF of a given cell. So we shall get to see how this is done appropriately. Let's take a look at the electropotential values of some metals. So we are looking at the electropotential values of some metals, and with these values we can ascertain the value, the electropotential of any given cell when two electrodes are used in constructing such a cell. So we shall take a look at some examples of how to calculate the EMF of any given cell. So looking at what we have displayed, we have a cell constructed using zinc and copper, and we can see the salt bridge between zinc and copper. So to calculate the EMF of this cell, we have it that the electrode potential of that cell is equal to the electrode potential for cathode minus electrode potential for anode. And we have said before that what takes place at the cathode is reduction, while oxidation takes place at the anode. So looking at the cell arrangement, it is clear from the cell arrangement that zinc to zinc 2 plus is oxidation, while copper 2 plus to copper is reduction. So what it simply means is this is right hand side, left hand side. So we said the standard electropotential is the potential of the right hand side minus left hand side, or we can say E cathode minus E anode, or we can simply say E reduction minus E oxidation. So this is actually how to calculate electropotential. So looking at that, it means that our E, the standard electropotential, is going to be the value for reduction. Reduction is copper, and we have it that copper is 0.34. That's positive 0.34 minus. The value for zinc is minus 0.76. So by the time we carry that out, this is going to give us 0.34 plus 0.76. And summing that up, we have 1.10 volts. So that is how to calculate electrode potential value for any given electrode and its electrolyte system, that is to say half cell reactions. Okay, that's for the first example. So let's take a look at the second example. In the second example, we are told to calculate the electropotential of a cell made with zinc, made with magnesium and iron. And we've been given their electropotential values. So looking at what we have here, we can see that between magnesium and iron, one seems to be closer to the positive part of the electropotential. Now, it is worthy to note here that when we talk about electropotential, that the value, as we can see here, when a value tends to go closer to the positive value, then that value is said to be likely to be the reduction potential. So between tin and lead, for example, we can see that lead is closer to the positive value. Hydrogen is 0.00, which stands as a standard and a kind of the bridge between the negative potential values and the positive potential values. So when a value tends to be closer to the positive value, the more likely it's going to be the reduction potential. So between tin and lead, for example, lead will be more the reduction potential than tin. So that is actually how it is. And looking at between two positive values, the one that seems to be higher will be the reduction potential. So this is actually how to determine which value is going to be the reduction potential and which value is going to be the oxidation potential. So between magnesium and iron, we can see that minus 0.44 is closer to the positive values. If we have our number line, this way, for example, 0, 1, 2, 3, 4, 5, this is 1, 2, 3, 4, 5, we can see that according to the number line, if we have minus 0.44 somewhere here, minus 0.44, and we have minus 2.3, as we can see for magnesium, 37, minus 2.37 for magnesium, minus 2, this is minus 1, minus 2, minus 3, minus 4, minus 5. So minus 2.3 maybe somewhere here. So we can see that minus 2.3 somewhere there and minus 0.44 somewhere there. So we can see that minus 2.3 is farther from being a positive value compared to minus 0.44. So minus 0.44 is much closer to the positive values than minus 2.3. So that tells us that the more likely you are closer to be a positive value, the more you get reduced. That is to be the reducing potential or the reduction potential. So what it simply means here is that iron is going to be our reduction potential, while magnesium is the oxidation potential. So magnesium will tend to lose electron easily, while iron gains electron. And when you lose electron, that is oxidation. Gain of electron is reduction. And we have said this countless times. So to calculate the E.M.F of that system, we have said that the E.M.F is going to be electropotential is E reduction minus E oxidation. Or we may say E cathode minus E anode, because at the cathode we have reduction taking place there, gain of electrons, and at the anode we have oxidation taking place there. So we can also say it is E right hand side minus left hand side, because reduction is usually written at the right and oxidation at the left. So what that should be is something of E standard electropotential is going to be reduction, which is ion. So the ion is the reduction, that is minus 0.44 minus the value for magnesium, which is minus 2.37. That's minus 2.37, yes, correct. So this is going to be minus 0.44 plus 2.37, because minus times minus is plus. So what do we have? With a calculator, we're going to have it as minus 0.44 plus 2.37 is the same thing as saying 2.37 minus 0.44. And we're going to have positive 1.93. So here we have our answer as E is going to be plus 1.93 volt. So it tells us that our value, our answer is plus 1.93 volt. This is how to calculate E.M.F of any given cell. That is the half cell for any given equation. So let's proceed to our next example. So let's confirm what we've just done, and this is what we're saying. So we can see that, and that is our answer, and that is perfect. So let's look at our next example. So we are told to calculate the value of the E.M.F for the reaction 2Ag plus ion to give us ion plus 2Ag plus. So how do we go about that? And we've been told that the silver electropotential is 0.8 and iron is minus 0.44. So how do we go about that? Now, looking at what we have here, it simply tells us that silver, since it's higher than iron or more positive, is going to be reduction, and iron the oxidation. That is simply what it tells us here from the values, as we have seen before. So the more positive you are, the more likely you're going to be reduced, that is, accept electrons. So, but we need to consider the equation. From the equation, we can proceed. Ordinarily, from the values given to us, silver should be the reduction potential, while iron the oxidation potential. But looking at the equation given to us, we will have to reconsider. We will have to reconsider what we should do. Looking at the equation given to us. So from our equation, we have it that 2 silver reacts with iron 2, and we have just the other part of solid iron and silver plus. So we can see we have iron solid and then 2 silver plus. So from the equation, it simply tells us that iron has been reduced while silver has been oxidized. That is what it tells us. So it tells us that iron will become the reduction potential and silver will become the oxidation potential. That is simply what the equation tells us. So we will go by the equation. This is actually how it is. So sometimes you're given a value, even though you know it should be this other way, but because the equation is saying something else, we ought to follow the equation. Now, what would be our E reduction? E reduction is iron, and that is minus 0.44 minus E oxidation. What is E oxidation? That is for silver 0.8. 0.80. So this is silver. So what will it be finally? E0 is equal to minus 0.44 minus 0.8. So this is 0.44, 0.80. So that gives us 4. Here we have 2. Take 1 over there. We have 1. So this is actually what is going to give to us. So we have minus 1.24 volts. So this is actually what we have, and is as simple as that. So when we have this, so it tells us that our E naught is going to give us a negative value, minus 1.24 volts. So it's giving us a negative value. So since it's giving us a negative value, then what it simply means is that we are having that, as we can see, the value is minus 1.24 volts. So it simply tells us that that reaction is not going to be spontaneous. That is what it tells us. It is never going to be spontaneous because the E value is negative. We shall come to see why we say it is not going to be spontaneous. So I would like us to take note of this. So sometimes when we are giving the potential value of these electrodes and we are given the equation, so from the equation we can calculate. Normally silver should be the reduction potential and iron oxidation, but the equation is not saying so. It simply tells us that the electrodes were changed. That is, where they ought to be, they were turned the other way. That is what it plays. That's just what it says. They were turned the other way. And since they were turned the other way, it means the cell that is going to be produced by this way, making silver the oxidation part and making iron the reduction part, it simply means that that cell is not going to work. That is simple. That is what it means. So it's not going to be a spontaneous reaction. That is actually the implication of turning these cells the other way around. Okay, so with that, we shall look at yet another example so that we can be well grounded in this.